and we got into a discussion of a certain thermodynamic property, which is known as entropy. And entropy, again, is delta S. Again, not to be confused with delta H, which is the enthalpy, delta H being the heat of a reaction. And again, we do see delta H a lot in this chapter as well. So as we talked about last time, again, our delta H is our enthalpy, really dealing with, as I mentioned, sort of whether or not, for example, the reaction is exothermic or endothermic, depending on whether or not we have a positive number, which would mean it'd be endothermic, or we have a negative number, which means it would be exothermic. And we then started talking about really delta S. And again, delta S is entropy. And delta S really does deal with the, again, usually we talk about it in terms of disorder. So the amount of disorder there is. And as we talked about last time, a little bit different in terms of delta S is as the amount of disorder increases, the number actually gets more positive. So a more positive number there that you have for delta S, the more disorder there is. Obviously, that means there's less order that's happening, and vice versa as the amount of disorder decreases, which by the same token would mean that the amount of order increases. We do see it becoming more negative. So common ways we could, very simply think about entropy, again, in terms of that is just phase changes. So we talked about solid, usually things in their solid state are relatively ordered with each other, especially, for example, if you have some type of ionic solid or something like that. It's a very long range order, and it has a very low entropy value, or more negative sort of entropy value than you would have in something that is in the gas phase. When we get into the gas phase, everybody's basically flying around, free from each other. There's obviously a lot more disorder because of that, and we would see a more higher value for entropy, again, probably going more towards a positive one. We can actually calculate two things when we look at entropy that we talked about. We could calculate the entropy or the delta S of the system, which is usually the reaction. Again, usually we're interested in the reaction that's taking place. That is usually our system in a situation like this. And to calculate the delta S of the system or the reaction, we basically just do products minus reactants. So it is a state function. So as we talked about last time as well, the only thing that's really important is sort of where it started and where it ended. And again, in a chemical reaction, where it ended is pretty much our products, and where it started is pretty much our reactants. So we do our products minus our reactants. We typically will find all these values in a table. We also, much like delta H and other sort of values, we do need to take the coefficients of the balanced equation into account. So we need to multiply the coefficient by the values that we find in that table. Now, we also talked about making sure it's important when you do go to that table, or really any thermodynamic table, that you not only, again, find what you're looking for, but you do find it in the correct state. So sometimes, again, there might be several different values for the same substance, and the only difference really is the state. One might be a solid, one might be a liquid, one might be a gas, or it might be aqueous. So you want to make sure, again, that you find the correct value. Also very different as well for delta S versus, say, something like delta H in terms of values in the table. You will find values for delta S for things in their natural state, like H2, O2, N2, metal and that type of stuff. So you'll actually find values. And also the values for delta S is typically all positive values. And the last thing that's important in terms of that is units. Again, typically when we talk about sort of final units for these guys, usually our delta H is something like kilojoules per mole or kilojoules. Our delta S is usually something like joules per mole. And the real important part here is the joules and the kilojoules. Again, here, they are different units. And sometimes, as we'll see, especially coming up here, that we'll have to use these values together. So we want to make sure, again, unit-wise, somewhere along the way, you need to usually do some type of conversion to get everybody into the same units. So to calculate our delta S of the system, like I said, it is our products minus our reactants. We also talked about the effect of the surroundings, and the surroundings are affected by the actual system. So, as we talked about, in sort of a regular temperature situation, a normal temperature situation, in an exothermic process, that system's going to give away all that heat and energy to the surroundings. And what that's going to do to the surroundings is it's going to pick up all that heat and energy. That means, say, gas molecules, air molecules, whatever may be flying around in there. It's going to have a lot more energy, going to be flying around a lot more faster, if you will. And it's going to usually increase the entropy of the surroundings. And that's vice versa. If a reaction is endothermic, that means it pretty much needs to draw all the heat and energy out of the surroundings. And when it does that, everybody in the surroundings now has lost energy and wouldn't be moving around as fast. And we would expect the entropy of the surroundings to actually start to decrease. And to calculate the entropy of the surroundings, it is minus the delta H of the reaction divided by the temperature in Kelvin. That minus is really important because it's basically an opposite relationship that we see. And basically, what I mean by that is what we just talked about. If the reaction is exothermic, we will get a negative value, which gives us a positive value for the surroundings, which means increase in entropy. And if the delta H is positive in an endothermic process, we would have a positive and negative value, which would give us a negative value for our delta S of the surroundings. So there's sort of that opposite relationships. Remember that neither of those values, the delta S of the reaction or the system, are the delta S of the surroundings, will actually tell us whether or not a reaction is spontaneous or not. In order to do that with delta S, we do have to look at what we talked about last time, which is the delta S of the universe, what we actually see here on the top of the screen. The delta S of the universe is when we take the system plus the surroundings. And at that point, if we do get a positive number for the universe, that would indicate that the reaction would be spontaneous. If we obviously got a negative number, it would be a non-spontaneous process. And if it equals 0, we would have sort of an equilibrium process. Everybody's sort of holding, not too much is happening. And lastly, remember that if something is spontaneous, it does not necessarily mean that that reaction occurs super fast. Again, it could occur fast, it could occur slow. What it means, when we say something is spontaneous, is under those conditions, we would expect this reaction to take place. Again, it could take place really fast, could take place really slow, but at some point, these are conditions that would allow it to basically take place. Any questions on any of that there? Okay, so where we're at is with Gibbs free energy. So we got to use a different letter of the alphabet here, and this is delta G. So delta G is what is referred to as Gibbs free energy. And pretty much it is kind of like what the name implies. It's basically energy that's available to perhaps do some type of work. So Gibbs free energy is sort of energy that's available to do some type of work. And we're going to see actually several different ways to calculate delta G. And I'll say it now, and we'll probably say it again a little bit later on as well. But really, you want to kind of choose the way based on sort of the information given to you in the problem. So based on the information given to you in the problem, there could be several different ways you may come up with a delta G value. Here is one equation, that one way that you could calculate delta G. The delta G equals the delta H minus T delta S. Our T here is Kelvin, our temperature in Kelvin. Our S is our entropy, and our delta H is obviously our enthalpy. This is actually the equation I was just talking about not too long ago, where we do have both of those values together, our enthalpy and our entropy, and this is where people mess up on units. So again, this guy is typically in kilojoules, this guy is in joules. So somewhere along the way, you're going to need to do a conversion. Otherwise, again, you're going to be off by that factor of 1,000. So, in the end, it doesn't really matter which way that you do it, but I will say in terms of units, our delta G also usually will end up in kilojoules. So these are the typical units that we have for these sort of three thermodynamic values. Kilojoules for our delta G and delta H, joules for our delta S, again, are the typical units in terms of energy that we associate with it. Now, when we calculate delta G, we actually can use the delta G value to determine whether or not a reaction is going to be spontaneous. And if the delta G is negative, which means it's less than 0, so delta G here is negative, the reaction will be spontaneous in the forward direction. So the way the reaction is written, we would expect that reaction to take place. We would expect it to go from reactants to products. If the delta G is positive, that means that the reaction is non-spontaneous. And it's non-spontaneous as it is written. Although if we did reverse the reaction, it would be spontaneous going the opposite direction. So as we will see here, and probably as you remember from delta H, if you take a reaction and you reverse it, you basically change the sign. So if we have a delta G where the reactants going to products is positive, and we reverse that reaction, which means our products become our reactants become our products, we will end up with a negative delta G for that reaction, basically because we reversed it, and it would be spontaneous in the opposite direction. And if delta G is equal to 0, that means that we do have a reaction that is at equilibrium at that point. So let's start with delta G of the reaction. Again, sometimes the system here. And we can calculate delta G naught. Again, as we talked about last time, typically speaking, when you see these sort of knot areas here, those are usually sort of standard conditions. And as you can see here, we talked about last time, I think, as well. If we're talking about sort of standard conditions, if we're dealing with any type of gases, those guys should have a pressure of 1 atmosphere. If we're dealing with any type of solutions, it should be 1 molar. And typically speaking, it is, as you can kind of see down here, 25 degrees Celsius in terms of the temperature. Those are usually sort of the situations we're dealing with, especially when we look up values, usually in tables. These are sort of our standard conditions. So usually when you see that, it's under standard conditions, when you see that little knot, and all those things are sort of in effect. So one way that we calculate delta G naught is basically just like we kind of do with everything else. You basically could go products minus reactants. So we could take the delta G is our delta G of our products minus the delta G of our reactants. And again, these would come from a table. So we would look up the table, and just like we've done before on these type of calculations, we do need to take the coefficients into account. So we need to multiply that by the values that we look up. Again, here we do want to look up values for both the substance and the state, like we talked about. So when we look up these values, these are sometimes referred to as delta G naught F of formation, or the standard free say that again, the standard free energy of formation. I'll spit that out, I think. So delta G F is typically what we find in those tables. So there's sort of formation of each of these sort of elements, and it's basically the change that occurs as we form these guys in their sort of standard states. So again, here you'll look up the delta GF values in the table, and you take products minus reactants, taking our coefficients into account. Now, much like delta H, when you go to that table, you will find zeros for things in their kind of stable standard state. So any sort of elemental form of something that's uncombined, so things like H2 again, O2, those type of things will again be zeros here. So for delta H and delta G, those type of things are zeros. For delta S, again, you will see values like we saw the other day. And again, we would do our products minus reactants, remembering to make sure that we do look up things in their right state. So this is, again, one way that you could calculate delta G, and this would obviously be the way you would want to calculate it if you pretty much were given nothing other than the reaction. So you're just sort of given the reaction, no other values, and you're asked to calculate the delta G. Probably you would go to the table, do products minus reactants. And that's a little different than, say, this guy that we saw here. Obviously, we would want to use this equation if you were given something like the delta H or the delta S. this is probably the better equation to use to calculate delta G. So again, there's going to be several different ways. We'll see a couple more ways before we're done here to get to delta G. But you typically kind of want to choose which formula sort of matches the information given to you. And that's a good way to sort of approach it without having to sort of reinvent the wheel all the way across with all these calculations. So why don't you take a second here, the delta G values there from the table are on the bottom. Why don't you calculate the delta G not for this reaction and figure out, is it spontaneous? So take a couple minutes there and see what you come up with. Okay, so let's take a look here. So again, if this was sort of a problem that was given to you, and you pretty much have the equation here, and you want to calculate the delta G naught of the reaction here, and that's all you're given. Again, you would go to the table in the back of your book, for example, is where you can find these tables, by the way, and you would look up these values here. Again, we want to basically do our products minus our reactants. So we want to go delta G of our products minus our delta G of our reactants. Again, we want to make sure we take the coefficients into account. So delta G naught of our reaction would be our product side. We have 12 CO2s, so each CO2 is minus 394.4. We're then going to add that to our other product, which is water. So we have 6 of those at minus 237.2. And that takes care of pretty much all of our product side. We're then going to subtract it from our reactant side. And that is 2 times our benzene there, 6C6H6. So 2 times 124.5, as these are our delta G formation values. And we don't see a value there for oxygen. Again, here, oxygen is going to have a value of 0. So if you see a value not given to you, and it's something like that, it is going to be 0, basically. Again, in its standard state is what that is. So doing all that, it looks like we do get 12 times minus 394.4 plus 6 times minus 237.2, and then subtract it from 2 times 124.5. Looks like we end up with something like minus 6405 kilojoules here. Any questions on that calculation there? So at this point, when we look at that number, we do see that it is negative. So our delta G naught is negative, and that means that it is going to be a spontaneous reaction in this particular case. Again, we can use the delta G value straight up to determine if it is going to be spontaneous or non-spontaneous. Any questions on that there? So again, you'll sometimes see, like I said, delta G naught of formation, and that's basically the values that you find in the table in the back of the book, for example, of these guys. So that's usually what the table values refer to when you see it labeled delta G naught of formation. So when you see that, that's basically your table values for delta G values. So again, in a problem, if you're given something and it says this is the delta G naught of formation, that's basically like what you would find in a table. Any questions on that there? Okay, so in a chapter like this, unlike a lot of other chapters, there's usually a lot of questions where they oftentimes will not even sort of give you numbers, if you will. They may just say, hey, this guy is positive, this guy is negative. Would we expect this reaction to be spontaneous or non-spontaneous? So in this chapter, you'll come across a lot of questions where, they really won't sort of give you values, but they'll give you maybe the signs of things, like this is positive, this is negative. And they really want you to sort of think about, what does that mean? What would we expect to happen? So looking at this equation here, that really ties together our enthalpy and our entropy together. We could actually look at this equation, and if we know really just sort of the signs of delta H and the sign of delta S, we can make a pretty good prediction in terms of what we think will happen in terms of this reaction and whether or not it would be spontaneous or non-spontaneous. So would it be spontaneous or non-spontaneous? So for example, if we look at this equation and our delta H was positive and our delta S was positive, we would expect this reaction to be spontaneous at high temperatures. At low temperatures, the reaction would be non-spontaneous. So let's think about why that is. So if we have a positive number here, so this is going to be positive. And if we have a positive number here, this overall thing is going to be negative, basically. So because it's subtracting, what that means is, if you remember, this guy, though, is in kilojoules. This guy is in joules. So the guy there, delta H, is basically 1,000 times, got kind of a 1,000-fold jump on it. So in order for our back end of this equation to basically overtake our front end with where our delta H is, we would need a really high temperature here to get our negative part to be higher. And again, that's why we would expect at really high temperatures that it would become spontaneous. But at normal sort of lower temperatures, we're just not going to get this back part of the equation to be larger than the delta H value, which is positive to begin with. So when we have sort of that situation of positive and positive, we would expect, again, our reaction to be spontaneous at high temperatures. At low temperatures, probably going to be non-spontaneous the way it's written. But if you reversed it, it would be spontaneous going in the opposite direction. Now, if we had a combination where our delta H was positive and our delta S was negative, what that's going to do is we would have a positive value here minus a negative value here. And that then would turn this into a positive number and a positive number, which means no matter what you do in that situation, the reaction is, or the delta G is always going to be positive. which means this reaction is non-spontaneous at all temperatures. So at all temperatures, when you have a positive delta H and a negative delta S, you're going to end up with a positive delta G, and the reaction will be non-spontaneous really at all temperatures. Now, if we have a negative delta H and a positive delta S, what that means is this guy will now be negative minus a positive. That means that's a negative and that's going to be a negative, which means at that situation, we will end up with a negative delta G no matter what we do, no matter what the temperature is. And that means that the reaction will be spontaneous at all temperatures. So at all temperatures, the reaction will end up being spontaneous because it will always lead you to a negative delta G. And sort of the last combination that you possibly could have is if you have a negative value for delta H and a negative value for delta S, again, negative here minus a negative, that's going to give us a negative and a positive value. So at this particular case, in order for the reaction to be spontaneous, we want it to be low temperatures. So we would need low temperatures here. And that's because at low temperatures, that will keep our positive value less than our negative value. And that will give us a negative value for delta G. At high temperatures, the reaction will be non-spontaneous. That is because at high temperatures, that's going to make our positive value here bigger than our negative value, and that will lead us to a positive delta G. So again, it's very common to sort of just use a formula and try to predict whether or not you expect the reaction to be spontaneous based on the signs. You obviously can't just, if you want, just put some numbers in there, make up some numbers, and see what happens. But again, you could really look at this equation. You could look at those signs for delta H or delta S and make a pretty good sort of guess or estimate as to what you would expect to happen, really based on the temperature that we see here. So again, two positives will be spontaneous at high temperatures. Positive H, negative S, going to be non-spontaneous at all temperatures. Negative H, positive S will be spontaneous at all temperatures. And two negative values going to be spontaneous only at low temperatures. Any questions on how to sort of use that formula to figure those things out? Okay, so let's take a look at a reaction here and actually maybe use this formula here. So in this reaction, this decomposition reaction of calcium carbonate, we're making some calcium oxide and some CO2 gas. And if the delta H for this reaction was 177.8 and the delta S was 160.5, what is the delta G not at 25 degrees? So why don't you take a second and calculate what the delta G value would be at 25 degrees and also predict whether you think it will be spontaneous or non-spontaneous. So take a couple of minutes here and see what you come up with. Okay, so if we are looking at this one here for 25 degrees, so again, in this case, we're given the delta H. We're also given the delta S values. So again, it wouldn't make sense to try to do products minus reactants here. We would want to use our formula here that we just saw here. And if we plug this in, I'm going to take 177.8. I'm going to times it by 1,000. And again, here, I'm going to do that because my delta S is in joules. So that will convert me into joules. Again, you can convert the delta S into kilojoules if you want. So either way you want to do it, really will sort of come out the same. Minus T, again, remember that we do need to convert that into Kelvin. So that is 298 Kelvin. And because I converted my delta H into joules, I'm good to go in terms of just putting our number in. Let's kind of go underneath it a little bit, 160.5 joules. And if we do all that good stuff there, looks like we get something like 130, 120 joules, or approximately 130 kilojoules, which again, our delta G is typically given in kilojoules here. First off, any questions on that calculation? What that calculation should tell us is here we have a delta G that is positive, which means at 25 degrees Celsius, this reaction would be non-spontaneous. And if you think about what we just talked about in terms of this formula here, we had a delta H that was positive. We also have a delta S that was positive. And as we talked about last time, when we have that positive and positive thing, we would expect it to be non-spontaneous at low temperatures, only spontaneous at high temperatures. So 25 degrees Celsius is kind of normal temperature, so that's not considered a high temperature. So this is what we would expect to happen based on the signs that we see for each of those things and the temperature. Now, can we figure out though that, at 25 degrees, it's definitely non-spontaneous? Can we figure out at what temperature it actually will become spontaneous? And we actually can. So if we wanted to kind of figure out, what temperature would this reaction become spontaneous? We could actually use our same formula here. Our delta G is our delta H minus T delta S. What we do know is in order for it to become spontaneous, we need a delta G that is negative. And if we just think about a number line, negative usually happens, past zero. So if we set our delta G equal to 0 here, and we get delta H minus T delta S, and if we rearrange this and solve for T, T would equal our delta H divided by our delta S. And again, we're bringing that T delta S to the other side, and we're dividing by the delta S back over. And we can put our numbers in here. Again, we're going to have some issues with units. So here I'm going to also convert my kilojoules into joules by timesing it by 1,000. And we're going to divide it by our 160.5 joules per Kelvin. And if we do all that good stuff there, 177.8 times 1,000 divided by 160.5, that gives us something like 1,108 Kelvin, which if we sort of subtract 273 from it, gives us 835 degrees Celsius. So what that number represents is the minimum temperature that you would need to reach in this particular reaction for this reaction basically to be spontaneous. And I would classify 835 degrees Celsius as a high temperature. And again, that is also what we would have predicted based off of the signs that we see for delta H and delta S in this particular reaction. First off, any questions on that calculation there? So this equation here, as you can see, is kind of useful. You can, in certain situations, figure out if a reaction is non-spontaneous, what sort of temperature you need to hit to actually make it spontaneous. And that's what we actually see here on this graph. So this graph is the pressure of CO2. And because CO2 is the only gas present, and it is a product, in order for it to have pressure, we would have to produce it, which means this reaction would have to happen, or sort of happen to our product side. And we see it's pretty much nothing happening here in terms of the pressure, but we do start to see at 835 degrees Celsius, we do start to see pressure there. And again, that's when this reaction would turn spontaneous. Now you may say to yourself, hey, there's some activity happening here and before 835, and you're right, there is some CO2 being formed before 835 degrees Celsius, but it doesn't really reach sort of standard pressure conditions until about 835 degrees Celsius. Remember, standard pressure, as we've been talking about, is 1 atmosphere. So for it to sort of reach that sort of standard pressure condition of 1 atmosphere, that occurs somewhere around there, 835 degrees. Again, in order to get to that, you got to start making some gas molecules right before that, because the more gas molecules you make, the more pressure we have, the increase in pressure we're going to see in this particular case. Any questions on that? So why don't you try one here? For the following reaction, delta H is minus 1204 and minus 216 at 25 degrees. Are the reactants or products favored here? Okay, so here again, in this particular case, we are given the delta H and a delta S. So that equation that we've been looking at is probably your best choice here to solve. Um, so that means our delta G naught would be our delta H. Again, you got some unit issues here, so I am just going to multiply it by 1,000 to get our delta H into joules. I'm going to then subtract it from our temperature, which we do need to convert to Kelvin, and our delta S there, which is minus 216.4. And if we do all that good stuff there, let's see, minus 1204 times 1,000 minus 298 times minus 216.4. Looks like we get something like negative 1.14 times 10 to the 6 joules, or if we convert it into kilojoules, which is what delta G usually is, minus 1140 kilojoules here. Again, here we did hit a negative value for delta G is negative, and that should mean that this reaction is spontaneous. And again, if a reaction is spontaneous, that means it should be heading towards the product side, right? So it should be happening the way it's written, going from reactants to products. Any questions at that? This again, like we've been talking about, could have been predicted as well. Our delta H was negative. Our delta S was negative. That's turning our negative and the other guy into a positive. So again, here at low temperatures, like we talked about, which 25 degrees would classify, we would expect it to be spontaneous because at that low temperature, the positive part of that formula is less than the negative part. So that gives us our negative delta G that we did calculate. Any questions on that there? So there is, as we talked a little bit about, I think at the very end last time, about entropy, for example, there is sort of a change in entropy that occurs as we change phases, and what happens sort of in terms of free energy at phases as we go from, say, solid to liquid, liquid to solid, and so forth. So when we go from one phase to the next, and just a reminder that, if we draw sort of a classic kind of heating cooling curve, if you will, and let's just say that this is the gas phase here, this is the liquid phase, and this is the solid phase here, and this is like temp. And, for example, if this was something like water, this would be 0 degrees Celsius, right, as it goes from solid to liquid. And again, if this was something like water, this would be 100 degrees Celsius, where it goes from liquid to gas. At these actual phase changes, they do occur, as hopefully you remember, they do occur at the same temperature. So when we go from solid to liquid, or liquid to solid, that basically occurs, at the exact same temperature. So, for example, water is 0 degrees Celsius where that occurs. And in the case of something like water, it's really not until you get a little bit above 0 degrees Celsius that you get liquid water, not until you get a little bit kind of below 0 degrees Celsius that you get sort of solid ice. Kind of right at 0 degrees Celsius, you have basically sort of both phases in equilibrium with each other. So you got like ice crystals, for example, solid and liquid together. And same thing happens over here, say something like water, not again to get a little below 100 degrees that you have liquid water, a little above 100 degrees that you got sort of gas happening. But right at 100 degrees Celsius for something like water, you also have both phases in equilibrium with each other. And as we sort of touched upon the other day, there's a certain amount of energy associated with doing those transitions. So, for example, delta H of fusion is the energy that's required to go from solid to liquid. Again, our backwards liquid back to solid. Not changing the temperature or anything like that, but for example, for water at 0 degrees Celsius, to take ice at 0 degrees Celsius to liquid water at 0 degrees Celsius, and vice versa, going from liquid water back to um, ice at 0 degrees Celsius is also the heat of fusion. And again, it really depends on sort of what you're doing in terms of energy as to what you will see. So if you were going from solid to liquid, you need to put energy in, and that would be endothermic. And our delta H of fusion would be a positive number. By the way, for water, it's something like 333 joules per gram, give or take. If you were going from liquid back to solid, you need to release that energy, right? And our delta H of fusion would actually be the exact same number, but it would be negative in that case. So, like negative 333 joules per gram for something like water in that particular case. Same thing occurs over here at our transition as we go from liquid to gas. Again, there's a certain amount of energy required, basically just to do that, just to do that transition and take something from liquid to gas. Again, not changing the temperature, our gas back to liquid. Again, that happens at its normal boiling point, right? For a substance is basically when that happens. Um, and that is what is known as the heat of fusion. I'm sorry, the heat of vaporization. The heat of vaporization is the energy required to take something from liquid to gas or gas back to liquid. And the same sort of process occurs if you're going from liquid to gas, you need to put energy in, and it's endothermic. Delta H of vaporization would be a positive number. By the way, for water, something like 2260 joules per gram, give or take. And if you're going from gas to liquid, again, their delta H of vaporization is going to be negative or exothermic in that process. And that's going to be something like negative 2260 joules per gram. And again, that's specific for water. Obviously, if you're not dealing with water, it would have different values for delta H of vaporization, delta H of fusion, and also the temperatures at which this occurs would be different. For water, this is 0 degrees Celsius we're talking about, which is the normal melting and freezing point, while for water, it's 100 degrees Celsius, which is the normal boiling point when this occurs. So, how does this relate to sort of our Gibbs free energy and also our uh, delta S, for example? If we look at our equation, our delta G naught equals delta H minus T delta S. Because this is an equilibrium process as we do these transitions, that means that our delta G naught is going to equal 0. Again, delta G naught will equal 0 at these sort of transitions. Again, because they're in equilibrium, that gives us delta H minus T delta S. And if we rearrange this and actually solve for delta S naught, or the entropy, we end up getting something like our delta H, oops, said it, wrote it wrong. Try it again. Delta H. We get our delta H divided by T in this particular case. And this is a way that we could calculate the entropy change that's occurring as we go from these phase transitions. And if we were to do it for the transition from liquid to gas, that would be our delta S of vaporization. If we were doing our solid to liquid, or backwards, that would be our delta S of fusion in this particular case. Now, this equation here is the one I was talking about the other day. This is the one that looks just like the delta S of the surroundings, except that the delta S of the surroundings has a negative here, and this one does not. So it's very common people mess this up. They put a negative here when they shouldn't and stuff like that because they're remembering our delta S of our surroundings. So the delta S of figuring out our delta S of vaporization, delta S of fusion does not have that negative. The delta S of surroundings does have that negative that's there. So if we take a look at an example of this, if we're taking something like here and we're going from liquid to gas, that again is going to happen at its normal boiling point. And if we put it into our equation here that we just solved for, the delta H would be 40.79. This is the delta H of vaporization for water. And that's the same as my 2260 joules per gram, give or take. And this is our temperature. And you may go, where did I get that temperature? Well, if I take 373 and I minus 273, that is 100 degrees Celsius. That is our normal boiling point for water here. And again, that's the delta H of vaporization that's happening. And if we do all that, even though I just scribbled all over it, it looks like we do get something like 109 joules per Kelvin as our delta S of vaporization here. Now, let's see if this sort of makes sense based on what we kind of know about delta S. If I am going from liquid to gas, I would expect an increase in disorder, which means I would expect my delta S value to be positive, which it is here, right? So what would be happening if we actually went the opposite direction? If we went from gas back to liquid, right? So if we decided to do what happens with our delta S if we go from gas for water back to liquid water. This is also the process known as condensation, right? As we go backwards. In terms of our calculation, not much is going to change because it is still 4079 kilojoules, which is the heat of vaporization, over our 373 Kelvin. But the difference is when we are going in this direction, going from gas to liquid, our delta H of vaporization is actually a negative number, which means if we were specifically going in the opposite direction there, going from gas back to liquid, our delta H value here should actually be negative. And what that would give us would be negative 109 joules. And does this make sense for going in that direction, going from gas back to liquid? And it does, if you think about it. If we're going from gas back to liquid, the amount of disorder should start to decrease, which means our delta S should be a negative number, which surprisingly right there, it is a negative number. Some people might still call this the delta S of vaporization. Some people might call this the delta S of condensation, right? As we're going from gas back to liquid. Any questions on that? You could do kind of a similar calculation for solid to liquid or liquid to solid using the delta H of fusion. So again, a reminder though that although we oftentimes think about water as a very common example, if we're not dealing with water as a substance, we shouldn't be using like these numbers, obviously. We should be using the boiling point for that substance or the freezing point for that substance, and we should also be using the specific heat of fusion or heat of vaporization for that particular substance. Any questions on that there? All right, so why don't you take a second here and calculate this one. We're looking for the entropy of vaporization, so the delta S of vaporization in this particular case, given that information that you got there. Okay, so on this particular one here, again, we're talking about the transition going from really liquid to gas as we're looking for the delta S of vaporization. So again, taking our sort of formula there, our delta G is going to equal 0 in this case because we're at equilibrium at this case. Doing the same sort of rearrangement and dividing by T gives us this again without the negative there. And putting in our numbers here, we will end up with 58.5. I'm going to multiply it by 1,000 because delta S is usually given in joules. I'm going to divide it by 630 Kelvin. Again, here we can see we are not dealing with water, but we're actually dealing with mercury. So we have a different value for delta H and also obviously a different value for the boiling point that's there. And that does give us something like 92.9 joules. Again, here, this would be a positive number, which we would expect going from liquid to gas. If we were sort of talking about the condensation process here, the only difference is we would put the negative there for our exothermic part of our delta H, and we would end up with a negative delta S in this particular case. Any questions on that there? All right, we will wrap it up there for lecture here today for this. A couple reminders, obviously, like we've done before, the exam will open right around 11:30, and you should probably start right around 11:30 so that you get the benefit of all the time that's assigned there. Again, if you start too late, the computer might cut you off and you won't get the full time, and it will not be reopened for you. Just like everything else, they're the ones that are labeled that you need to show work. You obviously need to show all the work, the units, the setup, all that kind of stuff. And you need to upload that work. A reminder that once you submit your exam, you should upload the work pretty much immediately. So don't forget to do that. If you do, no exceptions, you will get zeros on those questions. So make sure that you do upload it right away. Make sure it's also, again, labeled so I could really identify what problem I'm looking at, and it's not just random kind of markings all over the place. Um, Reminders: closed book, closed notes, no notes out for any reason or anything like that. Closed people, no other people as well, or any of that type of stuff. Obviously, when you're taking it. Let's see. So same sort of format. You'll have to go through the module there, do the academic honesty agreement. That will open up the exam. Take the exam. Make sure you hit submit only once. And then you could upload your work. That should open up that one. Make sure that you do read the instructions. There are specific instructions on each question as to how you should enter the answer. So please make sure that you follow the format that it shows you on the question. It should you should probably not enter units online. It doesn't like really units, so don't enter units, but make sure you do have the units and stuff like that on your paper that you upload. Everything that you need, I think, should be there. You have a periodic table, which again you could open. I think you got some conversions there as well that you need, and any type of constants. I think you should have everything that you need. For any reason you have any questions or anything like that, you can email me. But again, like I said, I think it's pretty self-explanatory and stuff like that. Also, a reminder to make sure that you upload the textbook homework as well. So that should be up there for you to upload if you haven't done so already. And obviously, the last reminder would be the buffer lab. So I think I went through most everybody that submitted it. So make sure you check it, make any corrections if you needed to. Some didn't have any corrections to make, so you're obviously good to continue on. But make sure you take care of that. Again, officially, all the rest of the sort of the stuff, I guess the completed lab report, if you want to call it that, was next Tuesday it's due. So make sure, again, that you work through that. If you need to resubmit, make sure you resubmit. And, over the weekend and the next few days, I will obviously continue to check it. So you should continue to check it as well. Any other questions on any of that stuff? I think on Tuesday as well, we will start the next experiment, which is titrations, I think. So that's what's coming up next in terms of lab. And obviously, we will continue lecturing on this and probably roll into the next chapter, which I think might be electrochemistry at that point. Any questions on anything like that? Again, make sure you are using Proctorial. Make sure, again, you do the best that you can do to make a show, not just your head, but perhaps your work area as well. Other than that, have a good weekend. Good luck on your exam. And again, if you do have questions during the exam, you can email me. But I think it should be pretty self-explanatory, but feel free to email me and I will get back to you. All right, I'll see everybody next week. And don't forget to take the exam and upload your work.